Hello students. So CV characteristics of the MOSFET. Previously we did the band bending. I explained you the basic structure of the discrete band and how the band structure becomes when the MOSFET you are bringing the metal oxide semiconductor together. So now today what we will do is we will study about the CV characteristic of the MOSFET. Okay. Now this CV characteristics basically what does it explain is how the capacitance of the MOSFET changes when the gate voltage is changed. Now, now what I am going to explain here is that for a P substrate, okay. So first I'll write it here very clearly so that there is no confusion in between. So P substrate, 1 minute. Yeah. So this will be a P substrate N channel MOSFET, okay. P substrate N channel MOSFET. Now here you can see that if we take a P substrate N channel MOSFET, the structure will look somewhat like this. This will be my P substrate and there will be two pocket of N. Okay. And here there is some insulator and then there is gate. Now this is P substrate. So that means there are more holes than the number of electrons. Now in order to make a channel here, you need to give what type of voltage to the gate? You need to give to the gate positive voltage. Only then electrons will be attracted at this point, right? This much you understand from very preliminary. Okay. Now what happens that even when Vg is equal to 0, in this condition I am explaining, even when there is Vg is equal to 0, that time there is a band bending there. The band is bended. Why this band bending is there? Because of the difference between the semiconductor and the metal work function, psi ms, there because of this value here. And whether the band is bended upward or downward, that will depend upon the substrate. Now here you can see it is a p-type substrate. Now when Vg is equals to 0, what do you think must have happened? Just let us very quickly do the previous things what we have done. This is metal, this is oxide, this is semiconductor. Now in this case it is a p-type substrate. So in case of p-type substrate, EF, that is Fermi level, is near to the valence band, so it is down, and here the Fermi level of the metal will be there, right? So and this is, if I take this as the vacuum level, this is the vacuum level, then you can see that the work function of the metal is lesser than the work function of the semiconductor, right? Work function of the metal is less than the work function of the semiconductor. So psi ms is becoming negative, right? Psi ms is negative. Now when psi ms is negative, that means, what does that mean? That in order to avoid the band bending, in order to make the bands flat, you need to give a negative voltage on the gate. Getting my point? So in order to make the bands flat, or you can say to avoid any kind of band bending, you have to give a negative voltage on the gate. Now see, how does it happens? At Vg is equals to 0, that we have already said you that since this metal work function is lesser than this one, so actually there is no transfer of charge, but there is a redistribution that is happening, charge redistribution when the gate voltage is applied. This is happening to go towards the thermal equilibrium condition. Okay. So when we apply a negative gate voltage, say suppose the negative gate voltage when we apply, then a charge redistribution takes place. So what will happen, that you are applying a negative gate voltage that will repel the electrons and from the interface. So it was going to, if you take this structure, now here it is N, here it is N, and this is your gate. This is the insulator, this is your gate. You apply a negative voltage, so it will repel the electrons. Electrons will be moved here. Okay, and the positive charges will be attracted. So electrons will be repelled away from the surface towards the bulk. Okay, and after sometimes the positive charges will be attracted if you keep on increasing the negative voltage. So that will lead to a formation of inversion region. Now let us understand it more nicely with the help of the band diagram structures. Now see here, this is explained for the accumulation. So if you want the first let us understand what is the meaning of accumulation and inversion. And with the inversion, so with the respect of what we are calling it accumulation and inversion. So with the respect of substrate, not with channel. Okay. So here in P substrate, when the substrate is P type, that time the channel has to be created N type. So with respect to the substrate, the channel is N. So we say inversion has happened. But when the P substrate is positive, means holes are there, more holes are there. So in that case, when holes are only attracted, that time we say that it is the accumulation region. So here you see this point. What happens that when you give a negative gate voltage, when you give a negative gate voltage here, then it is going to repel the electrons and attract the positive holes. So when holes are attracted here, that is the band will bend upward. Okay, the band is bending upward. Now band will bend upwards when you are giving a negative voltage. Now from negative voltage, now just see this previous one figure. 1 minute. Yes. So here what happens when this is the strong accumulation region, you have given the negative gate voltage. So this is happening in this part is happening when the gate voltage is negative gate voltage for negative gate voltage for P substrate. Okay. Now here when P substrate MOSFET. So here the gate capacitance is equal to the Cg is directly equal to C ox, that is the oxide capacitance. Okay. Now when you are moving, when you are giving the minus voltage to the gate, one time it will come that the bands will become flat. So this is the point where you have this is the flat band voltage. Vg is becoming equal to VFB. So Vg is when this Vg is becoming equal to VFB, that time you have the flat band condition. So after the flat band condition, once you reach the what? The flat band condition. So that flat band condition, all the bands will be flat. Now, if you start giving positive voltage to the gate, then in first what it will do when you give the positive voltage to the gate. So when you are giving the positive voltage to the gate, here it was N and N. So yeah, this is P. Now this will repel the holes because you are giving the positive voltage. So electrons will be attracted. First the holes will be repelled and then the electrons will be attracted. When the holes are repelled, we are calling it weak inversion. At that time, just the acceptor ions remain there. Means you are repelling the positive charges, so the acceptor ions are formed there. And then after that, when the threshold comes, at the threshold VTH, from that time the strong inversion starts. So when this part is there, the weak inversion part, what happens? The capacitance, you see this is decreasing. At this point, the strong accumulation point, the capacitance was equal to the oxide capacitance. And when it is coming, when you are giving the positive voltage to the gate, the capacitance is decreasing. Why the capacitance is decreasing? Because the oxide capacitance is coming in series with the depletion layer capacitance, because a depletion layer is created. What I said you just now, that see, this was your, I'm making it a little bigger. So this was your N type and this is P. This is N and N here. So when you are giving a positive voltage on the gate, then first the holes are repelled. So when the holes are repelled, a depletion layer is created. Okay. Depletion layer is created, means space charge region is created, and because of that, the depletion layer capacitance CD is formed. And this depletion layer capacitance is in series with oxide capacitance. And when two capacitances are in series, then the resultant capacitance decreases. So what happens? That the capacitance is going on decreasing, and at this point, it is reaching the minimum capacitance. Okay. At this point, it is reaching the minimum capacitance. After that, when if you increase the gate voltage, now the electrons are getting attracted to form the channel. At that time, little by little, again that gate capacitance becomes equal to the oxide capacitance, because the depletion layer capacitance, that time it will not, when you're because of the formation of the electrons, this depletion layer capacitance decreases, and then again the full capacitance will be coming equal to the oxide capacitance. That's why you can see that this level and this level is same. So let us once go through this in the format what I have written here. See, first I will explain you this part. This, I think you have understood this part from the previous explanation itself. still I'll just tell it. So first type is the accumulation region, where that's how to bring a accumulation in the p-type substrate. You will have to give a negative gate voltage. Negative gate voltage will attract holes and the bands will bend upward. Attract holes, it is redistributing the charge, it is not transferring. Okay, then in the next case, what happens that when you start giving the positive gate voltage, first there is a depletion of what? Depletion of positive charges. Okay, when you are giving a uh, when you start giving positive voltage on the gate, first the holes are repelled. So when the holes are repelled, that time a depletion layer is created. Then if you continue increasing the positive gate voltage, that time what happens that the electrons are attracted towards the semiconductor oxide interface. So here you see the oxide is getting collected. That time the band will bend downward. So for that, you can see over here, this is the band is bended upward. Band is bended upward because holes are there. Holes are getting collected at this point. At this point, there is nothing is collected, just the holes are getting repelled. So there is a space charge region. So this is the depletion region. Here it is happening with positive gate voltage in case of p-type substrate. All we are talking about right now is about the p-type substrate. Here you can see the intrinsic Fermi level. Intrinsic Fermi level is also bending and it is coming closer to the Fermi level, the Fermi level of the semiconductor, but it has not yet passed. Once the electrons getting concentrated here, that time what happens that the EFI, the intrinsic Fermi level, is crossing the main Fermi level, and this portion means the this is p-type, the bulk portion is p-type. So, and the semiconductor oxide interface means the junction here, this is becoming uh, populating with electrons. So this is becoming n-type. So this will become as much n-type as inside it is p-type. So that is the reason of strong inversion. And at strong inversion, the capacitance is the full capacitance of the MOS will become equal to the gate capacitance. So you can see in this structure that again, in here you can see that again this level is matching this. So at the start, the capacitance was equal to the oxide capacitance. When the inversion started, because of the formation of the depletion region, the depletion layer capacitance becomes in series with the oxide capacitance. So the capacitance reduces. And now what happens, because of the low frequency characteristics, here this region is the high frequency curve. Okay. Now here as we are going towards the strong inversion, we are reaching in the low frequency region. And that time also the depletion layer capacitance is decreasing. And finally it becomes equals to the oxide capacitance. Now let me explain with the help of this. This figure is the high frequency CV characteristics of the MOS capacitor on a P substrate. It shows how the gate capacitance changes as the gate voltage is swept from negative to positive. So when you apply a positive gate voltage, small AC signal is applied, it is written here, means basically you are applying a small positive voltage. Sorry, for P substrate, what you need to apply for accumulation is negative voltage. So the negative voltage is applied so that first the bands can be made flat. So when the bands are made flat, how to make the bands flat? Whatever the built-in potential was already there. So those built-in voltage has to be overcome. You have to overcome the built-in voltages because of the psi ms and the VOX0. You have to overcome these two. So to overcome these two, the flat band has to be reached, and to reach the flat band, you have to give the negative gate voltage. So negative flat band voltage is there. The gate voltage is equal to minus VFB. So at this point, this is their flat band voltage equation. So that is equals to metal semiconductor work function difference minus QOX by COX. That is the potential of the oxide. Oxide potential. Now, at this point, for ideal MOSFET, there should be no oxide capacitance, there should be no trap charges, but this doesn't happen. So what is the equation that we give is psi ms minus QOX by COX. This is basically VOX0. So for a P-type substrate, the VG is less than VG is less than VFB. What does that mean? Gate capacitance is less than flat band. Means basically here it should be written that flat band voltage is negative. For a P-type substrate, gate is made negative. Flat band voltage is negative means you are giving gate voltage initially negative to reach the flat band, right? To reach the flat band, you are giving gate voltage as negative. So at negative, gate attracts holes. Okay. holes accumulate near the oxide interface and the bands, because holes are accumulating at the oxide interface, so the bands will bend upward. So that is shown here. So this you can see here. The band is bending upward because the holes are accumulating. Next, what happens? Holes accumulate, new bands bend upward, large hole concentration at the surface, but still no depletion layer exists. So all the voltage drop across the oxide, and that is why all the voltage drops across the oxide, and so this gate capacitance is equal to the oxide capacitance, and this is the maximum capacitance value. This explains the flat region on the left. The region which you have here, this flat region, this is the maximum gate capacitance. Okay, now oxides behave like a capacitor. So for the oxide, the formula is this: epsilon OX into area divided by the thickness. Since semiconductor behaves almost like a conductor due to abundant holes, only oxide contributes. So here only there is a contribution of the oxide capacitance. Now what happens as Vg is increased? So right now your Vg was negative. Now first it reaches the flat band. Now at Vg is equal to Vb, bands become flat. No electric field is there inside the silicon. Okay. No depletion, no accumulation. Just the flat band is reached. Now, after that, what happens? That Cg is equal to Cox, because depletion width is almost zero. Now, when you are making Vg greater than VFB, so we have started from first, it was between. So there were actually for us, there are three things. Flat band is there, right? Flat band is there, and then we have the uh, accumulation also. So the flat band condition, Vg for this p-type substrate, we are giving Vg negative. Now, when VGS is less than VFB, that time it is the accumulation. And that can be strong accumulation if it is very far from the flat band. Okay. Now, when VGS reaches equal to VFB, VGS is equal to VFB, that is your flat band condition. Okay. Flat band condition. And after that, when VGS is greater than VFB, VGS is greater than VFB but lesser than VTH, that is your depletion state. In this state, the capacitance is decreasing. At this state, the gate capacitance is equal to the oxide capacitance. Here also the gate capacitance is oxide capacitance. But at this point, the gate capacitance is the series of Cox and CD capacitance. Where is this depletion capacitance coming from? The depletion layer between the source and the p-type and the drain and the p-type, that is creating the depletion capacitance. So we will increase the gate capacitance till so as depletion width increases, CD and CG, drain capacitance and gate source capacitance, you can write here, decreases, and that is the reason first the depletion layer capacitance increases and hence CG decreases. So this means this is telling about because the oxide capacitance and the depletion layer capacitance, they come in series. So the gate capacitance decreases as the depletion layer increases. And that is the reason the downward slope can be seen in the characteristics. So this is the characteristics where you can see the downward slope. Okay, this is the downward slope when what is happening at this point? Gate capacitance is equal to oxide capacitance plus depletion layer capacitance in series, and so the full capacitance is decreasing. Okay, now after this reaches the VGS, this was the condition when the gate source voltage, means the gate potential, was between the flat band and threshold. And in this case of P substrate, our flat band voltage was negative. So in between some negative and positive voltage, if you are putting this gate voltage, that time it is depletion. Now, once the gate voltage crosses is greater than the threshold voltage, then you reach the strong inversion. And before this, there is a value where VGS is equal to VTH. At that point, you have the inversion. This inversion starts at this point. Okay, so inversion starts means depletion layer capacitance now decreases. And how the band is bending? Because first it was bended downwards. Means first it was maybe this whatever was the reason from that We will start from flat band. First, it was if you are putting here the positive charges, see once here, if you put the negative charge here, the band is upward. Now, if you are increasing, means if you are decreasing this negative thing, then once first it will come towards the flat band, then it is going towards the uh, band bending downward in the opposite direction. Okay. Now, when you will increase it more, when you will make this more positive, that time it is going to cross the Fermi level here. The intrinsic Fermi level is going to cross the Fermi level. So that is the whole structure that you need to understand here. Now let me once explain you from the written things here. Okay. So see over here, what I explained is given here. This how these things are changing. So when Vg increases, band bending reduces. At Vg is equal to VAP, the band will become flat and there is no electric field, and that time the gate capacitance is equal to the oxide capacitance because there is no depletion layer actually formed. When you start giving the positive voltage to the gate, when you reach the threshold, that time in this condition positive voltage, okay, that time what happens? Firstly, the holes are repelled. So when the holes are repelled, that time the depletion layer is formed and that time the capacitance decreases. Once the depletion layer is getting formed, after that, what happens? The electrons are attracted. That is the time when the threshold voltage is reached. After threshold, the inversion is becoming strong inversion. Okay. So here the surface potential is becoming 2 times of psi f when it is the strong inversion is reaching. Okay, that time the surface potential is becoming between depletion and threshold, a few minority electrons appear, band bends further downward. This was the weak inversion phase. Now the surface intrinsic level crosses towards the Fermi level. Electron concentration starts increasing exponentially, means now when you are giving more gate voltage, more electrons are attracted, and when more electrons are attracted, depletion layer width gets reduced, and thus the capacitance is again going to increase and become equal to the oxide capacitance. So that's why the depletion width stops increasing, thus capacitance becomes equals to the oxide capacitance, and capacitance rises back towards that is the main thing, the capacitance is rising back towards the oxide capacitance. So this is about the CV characteristic of the MOSFET. So it starts with the high frequency characteristics, and this was for the P type substrate. Now, if it is N type substrate, the voltage here, that is the flat band voltage, will be positive here, right? The flat band voltage will be positive for the N type substrate. N type substrate means P channel MOSFET. Okay. So these are the things that you have to keep in mind. At this point, this is C aux. At this point, it is C aux plus CD in series, so the capacitance reduces. Here again, because when the electrons are getting attracted, that time depletion layer width is decreasing. So again the capacitance is increasing. The capacitance is going to increase, and finally it is becoming equal to the oxide capacitance. So once again, go through this notes and the video. So that will be useful. Thank you, everyone.